And welcome everybody for tuning in. So today MPC Markets is bringing you AI for Dummies, and we've got our resident IT expert Chen here, who will be the genius that will be demystifying for us, and then myself, Jonathan Tacadena. I'm the dummy in this case, and I will try and distill what Kai is going to explain in pretty much normal language. Okay?
So it's not as complex as you think. There's a lot of obviously implementation details if we really dig lower, but we're not going to try to do that today. Basically what we want to know is how it all works, and so you get a better understanding of what's possible and what's out there.
Okay, great. No worries. Well, that's a quick rundown, but first, before we do that, just a general advice warning. So everything we talk about today is just general advice and doesn't take your personal circumstances into effect, and if you want to implement any ideas from here. Sorry, it's just all education, but consult a professional first. Okay, so this is our agenda for today. So I will be briefly talking about the history of AI, just how we got here in early 2025. Then Kai will talk about a few of the nuts and bolts and some of the explanations. He'll be talking about neural networks, some of the language processing, transformers, large language models, Deepseek, which just came out, I think a week and a half ago and changed the game.
A bit of shock to the system, wasn't it?
Yeah, absolutely. And then the last thing is, where to from here, and will AI be sentient, which actually just means actual intelligent itself. So, history of AI. So AI actually has started back in Alan Turing's era. So he came about in about 1950. And what we want is a machine that can learn from experience. That's his actual first thoughts.
Yeah, I mean, he was basically the creator of computers. Right? In terms of compute, he's a legend in the field. And going back to the Enigma code, but he's more than that. The guy was an absolute genius.
Okay, well there you go.
But a lot of modern computation actually was, Turing was the pioneer in that. And he had enough foresight in terms of kind of go into the future and see that machines could get intelligent. And this is where all the Turing tests came about. And it was like, well, at what level is a machine truly intelligent?
Yeah, right? Exactly. So, okay, well, I'll just talk about that. So Alan Turing, the Turing test was in 1950. He basically said, if I'm having a conversation with a computer and I can't tell the difference between a computer and human, then the computer is intelligent. So that was his test back in 1950. And the reason why I talked about that now is that we kind of hit that moment in 2022.
Well, if it walks like a duck, quacks like a duck, is it a duck?
Exactly. And so there was actually a period between 1950 and sort of 1997 where it was like the AI winter. And what happened there is, obviously there were advancements in computers, but the thing with AI is that it needs a lot of data. And the whole infrastructure wasn't built yet for sort of the advancement. So the next sort of step was 1997. Deep Blue, IBM's Deep Blue beat Garry Kasparov in a game of chess. So Garry Kasparov, I believe he was like a 3-time grand champion or grand master, I believe that's the term, and IBM beat him there. In 2006, so that between the sort of the tech bust in 1999 and in 2006, just before the GFC. Deep learning was introduced. There was an actual paper that came out. In 2011, Watson wins Jeopardy, and in that case, Watson actually. So it may sound trivial because we kind of take everything for granted today with the internet. You kind of just type in everything, but Watson was able to actually get the input as a question and then actually find the right answer and actually won Jeopardy. AlphaGo. So for those that don't know, Go is so if you think of chess, it's a quite closed board. There's 64 squares and a limited amount of moves, whereas Go is just infinitely, just so much larger. I think it's like a 19 by 19 board, and there's just so many more combinations and permutations there.
So just to go back through a bit of history, right? So with the Deep Blue moment, basically. In chess, it's a solvable problem. You've got an 8x8 piece of board. In terms of computation space, right? You can, at any point of move on a chessboard, you can brute force calculate what is the optimal move. right? So I can go, okay, I moved this piece to here. What are all my possible next moves that are possible on the board? And you can actually optimize for the best reward for that, right? So this is classical kind of compute where, you know, Deep Blue, when he's playing Pax World, it's super slow, but, you know, like basically if someone makes a move, if a human player makes a move, the AI can calculate what is the best next move to make, right? The issue with Go is it's a much bigger ball, right? So from what I remember, the computational space in terms of requirements to work out every single move on a Go board is more than more than matter in the universe, right? Okay. So you can't.
There's a lot.
you can't do it by brute force, right? So and what basically, you know, the pioneers in terms of deep learning, and it's separate to LLMs. So large language models are separate to deep reinforcement learning, which is what AlphaGo did, right? So how it works is basically it's a tree search model, and what it means is basically you have an environment. So in this case, it's a Go board, and you have action as well as policy, and you optimize for reward, right? And all this thing does is basically trial and error. It's like how a human learns, right? Like as a kid, if I showed you a chessboard, you don't know how to play.
No.
And you've got to go through hundreds of examples in terms of how to play chess, right? This thing learns the same way. Through training, by playing thousands of games which these guys feed in the game data from, you know, human professionals playing, as well as simulated examples in AlphaZero, right? It learns the optimal policy, which means if you make this move, how much reward will we get? And at the end, we want to optimize for that. And basically that model stores the optimal weight. So every time that you make a move, it can search through the tree of possibility, not the entire space, but just certain segments of that with weightings, and it's able to make, you know, amazing moves. And, you know, the crazy thing about AlphaGo was that it's not just basically regurgitating strategies or going by playbook. What is amazing at it was actually that it was innovative in terms of they made moves in which no human has ever played.
Whoa.
Yeah, it's a 3,000-year-old game, right? So there's people in Asia, all over the world who go to Go school, and there's, you know, 3,000 years of literature in terms of the history of the game, right?
So the computers come in and innovate it.
Correct.
That's the key point there. Okay, great. So that's in 2015, which is only 10 years ago. And then in 2017, Google had a team called Google Brain. They introduced transformers. Now we're not talking the cartoon transformers. It's actually just another way of structuring the compute or the data within there. So in 2018, OpenAI came out with its first GPT using transformers to create the first large language models. And in 2022, OpenAI develops a user-friendly AI interface, and that was ChatGPT. So that's only 2 and a bit years ago. And I remember using that first ChatGPT, and people just freaking about how good it was. And then here we are, 2025, Deepseek came out, I think a week and a half ago, with their R1 model, which pretty much just slashed the computing needs and just upended the whole AI landscape there. And we'll talk about that a bit more. But obviously going back to the Turing test, we kind of take it for granted, but that was the original test is that if I'm having a conversation with the computer and I can't tell if it's human or not, we are here. So we reached that point in 2022, and that was for it was like available to everybody. That's what kind of opened the floodgates, so to speak. Is that obviously AI scientists were working in the background throughout all of this, but then ChatGPT was the first one where an actual friendly user interface came about, and everyone kind of just jumped on, and that's when the real sort of AI pushes.
I mean, the technology is really, and the idea has been around for decades, right? So
exactly. So Turing started in 1950, so we're talking a long time ago, and then the first iterations or neural networks were starting around 2006, 2007.
With machine learning, right?
What's that? 15 years ago. So it's amazing what's happening.
I mean, most of it comes back to the three well, there's three main players who, in the 90s and 2000s really pioneered a lot of work, right?
Mm-hmm.
So you've got Jeff Hinton, who used to work at Google, but he's much more in terms of now on the AI ethics, or not quite ethics, but just ensuring alignment with AI. So he's kind of a bit of an AI doomer, to be honest. But then you've got the opposite end of the spectrum, Jan LeCun. So he's the chief scientist at Meta. And then you got Yoshua Bengio. So those three really, like, in terms of the basis of large language models is all neural networks.
Yeah.
Right?
So let's just pop on the next page. So now, Kai, could you take us back? Look, what is a neural network and how they actually work in terms of AI?
Yeah. So with neural nets, right? Like, the core of the concepts come from actually human anatomy or from biology, right? So, as they always say, nature is the biggest inspiration. You've had a lot of time to optimize. But essentially, imagine a human brain, right? So it's made of neurons and synapses. So you have hundreds of billions of neurons within your mind, right? And all these neurons are connected by synapses, and these are the links between the neurons. Each of these neurons activate when, say for example, you have a thought or you process an image. You go, okay, this is a cat. There's a certain amount of neurons that activate within your brain, and they're connected through neurons. And in terms of how intense these firings intense these synapses fire, it represents an abstract concept.
Yeah.
Right. So neural networks effectively are the same thing, right? So it's constructed based off layers, nodes, and weights. So all it means is, imagine you have on one layer of this model 10 nodes, right? This layer connects to another layer, which has another 10 nodes. Interconnecting between each of these nodes are weights to represent these abstract concepts. And to make it easy to understand, for example, this has been used a lot in terms of image processing, and this is going back like 15, 20 years, perceptron, right? Like, it's machine learning has been here for quite a while. So if you take an image and put it into its pixels, so all the number representations of an image, that's the input, and you jam it into these layers of nodes, right? And when it passes through these layers, at the end, it can spit out what this image actually represents. So the classic one is like recognizing the image of numbers like 8, 9, whatever, but handwritten, right? And it's quite complex. If you actually think about it, deciphering what a number 9 or 6, it's actually quite complex because it can be written in so many ways. Or if even for like animals, a dog can be represented in this way, in this light. Very complex if you really break it down, right? But essentially what happens within these layers is abstractions appear, right? So through these layers, when you pass an image of a 9 through, it might be layers which represent edge, the sharpness of it, how many strokes there are, whatever it is, right? And it's abstract inside there. But that basically the weightings, the connection weightings between the nodes represent these abstract concepts. And this is basically all a neural network is, right? So, yeah, that's really the core foundations of all machine learning and LLMs to a sense as well. But LLMs is taking it to the next level with transformers. Transformers, is a layer above where they have different architectures of these layers, right? You can have 1 layer, 2 layer, X layer amount, forward feed, backward feed, all these things, right? And all transformers is an architecture of neural networks.
Okay, so you're basically saying that the neural networks, so I'm just going to try and interpret that, sure. They're the base of how, the simple architecture of how a brain works. Like basically...
Pretty much the brain.
Yeah. Okay, so that's the basics of neural networks. And then the next kind of sort of step in AI was language processing, because obviously you just briefly talked about image processing.
Yeah.
Next thing is obviously language processing, because that's obviously extremely complex. So the way I interpret it is that you got, let's go back to the example. So a chessboard, it's a 6x6, 8x8, fairly limited number of moves. Go, almost an infinite number of moves.
Yep.
Language, another whole mess upon itself. Because obviously, everyone talks in different languages. And you look at English itself. Every person speaks English in a different accent, things like that. So yeah. So how does AI do language processing?
It's very interesting. That's a very good example, right? Like, the classic one is like, for a human, it's very easy to process. If I say, what is closely related? A dog, a wolf, beach. You'd instantly be able to tell a wolf and a dog. But for a computer, it's not that easy, right? Like, how does a semantic actually come about? And that's the complexity of language, right? So before I go on to like Transformers was basically a thing that revolutionized it, but I'll go a little bit more into what Transformers are. But before going to Transformers, what's the basis which everything is using, right? So there's terms like token, embedding, transformers. What are they? So tokens, basically, it's just a breakdown of words, right? So like, for example, unbelievable, you can break down to un and believable. Again, it's just semantic word separation. Embeddings is a different concept where you're transforming the words actually into vector representation, so a numerical representation of what that word is, right? So I'll give you, and it sounds complex, but I'll give you a really simple example. The RGB map, right? So if I said to you 000, you know what, if you looked at color maps or, if you played anything around with colors, it's white, right? Or if I gave you like 255, 255, 255, it's black.
Yeah.
Right? But from that number representation, you can decipher what color that actually represents. So in that sense, basically you create a model where you're going from numeric to some sort of an object or representation of something. Right? And it's the same with language. So this is what embeddings is. You are converting words or tokens into vectors, and then it's much easier for a model to process, right? Because if you had imagine you had models with a huge amount of numbers. Computers can process that, but you can't really process words or semantics, right? So that's why it's important. And then you get to the third layer, the breakthrough, which is transformers. Transformers basically is a context. What it's trying to do is it's going, let me try to predict the next word given my context, right? So it's like if you feed it in a bunch of text and a prompt, what it will do is go, okay, what is the most likely next word that's going to come based on my context that's passed?
So let's just slow it down a little bit here because we're talking for the dummies here. So the way I see it in a fairly brute comment is that so language processing is that AI or the scientists were able to just break down language into usable formats for computers in terms of numbers.
Correct.
And that's the basics of it. It's like, and because they've got so many iterations and so much data now, they were able to just force feed so many numbers through brute force and actually come out with how they language process.
Absolutely right. So exactly representing numbers as well as the contextual transformers, which is the contextual part. So instead of looking at a small string of things, it looks at the whole context, and then it predicts the next token. So
okay, great. So that's I've just learned something there, but I knew the general concepts, but it's just interesting how language is processed. And then now, what's the next step after that? So we've decided the language. You're about to talk about how transformers, and then onto the large language model. So can you talk a bit more about how transformers? Break that down a bit.
So then obviously the next extrapolation is the knowledge feed, right? So all LLM it's like these models, they have like billions. Say for example the Deepseek newest model, their large model is about 671 billion parameters, right? So it's talking about basically all the weighting, the nodes in that model. So the ability to process information or to represent the world knowledge in a sense, right? So what these frontier labs do, OpenAI, Google, Meta, Deepseek, actually not quite Deepseek, I'll go into a little bit more, but basically these frontier labs, right? They've got all the information on the internet, everything on Reddit, everything on Wikipedia.
Yeah, exactly. Like massive libraries of data to learn on.
Correct. And this was the other breakthrough where it was called the law of scaling, right? Yeah. Who would have thought the more information you fed it to it, actually when you compressed it into these models, it represents some form of intelligence. So this was actually the breakthrough, right? Because when they found out that by feeding it more data, more context, more things, but doing that, the model actually got much smarter. This is why these frontier labs are spending billions of dollars in terms of jamming more information and training new models up.
So they got to a point where it was like, okay, so we've got enough data to beat people in chess.
Yes.
We now have enough data to beat people in Go. We now have enough data to decipher language. Now we have enough data to actually perform enough to become intelligent.
Yeah, I would separate the two things. Like with AlphaGo's reinforcement learning, it's a little bit different to what we have here in terms of LLMs, right? But yes, essentially yes. The more data you feed it, the smarter this model will get, right? So with language models, obviously, with coming GPT-3, it came out onto the scene, and it was brilliant, right? Like at that time, but looking back at where we are now, you go, oh wow, actually it was a pretty bad model. Like you think back to the 2 years ago.
Well, I mean, like it just shows how fast the whole thing's moving. Because I remember like MPC Markets is only about 18 months old at the moment, and I just remembered we were heavily using ChatGPT at the beginning.
Yeah.
And like there would be just a lot of mistakes, and be like, this thing's no good. But then now, like once you've learned the prompts and how to squeeze the execution out of it, like we find it indispensable. So and that's in that space of 18 months. So it's quite amazing. Yeah. So so in more simple terms, like how I'm interpreting it. So transformers took that whole languaging process to another level in terms of sectoring it off, or
no. So the transformers basically it allowed it to be contextual. Right? So the greatness of transformers is basically like you can give it a massive set of a PDF, right? And based off that context, it's able to be more precise in predicting what the next token is.
Okay.
Right? So that's what it's trying to do. So the training of these models are split into two parts: pre-training and post-training. Right? So the pre-training is what all the big AI labs are trying to do, right? So this is where we're talking about like Elon bringing 100,000 GPUs for XAI, or OpenAI using Microsoft. These pre-training these foundation models are really difficult to train because there's just such a massive amount of data. Imagine all the internet. All that text needs to be passed through into the LLM to be trained to reweight these models, because what it's doing is, imagine you pass through all this information. Every single time you pass this information through in the training process, it reweights the whole model.
So it's almost like it's like almost like how a human grows or learns. Yeah, it's like you go from baby stage to and what you'll find with humans is that like our absorption of knowledge or execution just obviously is exponential as well. Like, as a baby, it just takes ages to learn. We are a sponge, but what we're learning is very, very basic. And then obviously as we get older, our skill sets, what we learn is much more complex as well.
That's a perfect summary of like machine learning in general, right? Because basically all machine learning models, they're optimizing for one thing, which is efficiency loss. Loss. Right, so evaluation loss, and basically what it means is if you give it, this is in supervised learning, basically if you give it something, and this is supposed to be something, how close is that? It makes, the model makes a prediction. Let's just say, for example, you feed it a picture of an apple, right? And at the end, it spits out pear. It's not too far off, but it's far off. Right, so you have a loss in terms of information, in terms of your prediction versus what the actual outcome is, right? Now, if it came out an apple, you have a perfect response, right? So going through many trials and training processes, this model refines itself. It might say at the start, go feed this image, it goes pair, or it could be even worse. It could be like beach, or it could be like I don't know, spaceship, right?
Yeah.
So something that's completely unrelated, and that loss function is very far, right? But as you feed more information and as the weights get refined, this thing will be a very good predictor that this isn't happening. So this is the same concept in terms of LLM when you're training the process. That loss, like optimizing that loss function, where you're minimizing that error. That's the key, right? So these models basically it decreases exponentially in the sense like the more data and training you feed it through, the error gets lower, right? But it never obviously gets to zero because then you get true actual representation of the model.
Yeah. Okay, interesting. So that's transformers, and yeah. So I know Kai's talked already about it, but yeah, the next step was obviously the large language models, which is where we are in terms of AI development now. So can you've already talked a little bit about it, but do you want to just go?
Well, I think
go a bit deeper.
Yeah, I mean, like let's talk about who the frontier labs are, who's in the game, right? So obviously OpenAI came out 2 years ago with GPT, and you know it's funny because I think Google had all the potential to do that, right? They had all the scientists, they had all the capabilities. Transformers were invented at Google.
Yeah, so that's the Google Brain team, isn't it?
DeepMind.
Yeah, DeepMind.
Yeah.
But that was 2017.
Yeah.
Then a year later, ChatGPT came out.
Correct. Yeah.
So, not ChatGPT. Sorry, OpenAI came out with the.
Yeah. But the reason why it was so good was because it's interactable. Like it was usable, right? Because everything else before was basically off research. And I was listening to an interview with Demis Savas. So he's basically the chief scientist at CEO at Google DeepMind. He's the one who invented AlphaGo, right? Basically, he was saying that Google, we had this pretty much ready to go, but Google didn't want to release it because of inaccuracy. Right? So because it had hallucinations, because it wasn't accurate in terms of responses, Google was afraid to release it. So, but OpenAI took the risk, and the rest is history, right? But like we've seen everyone else catch up massively in terms of the space, right? So the other big players are Anthropic. Anthropic, if you've done their code, like the Claude models, it's included Perplexity as well. Meta is the one that I'm very bullish on in terms of.
So what's the architecture called? Llama, is it?
So their LLM, their foundation model is called Llama. Yeah, Llama. So basically they've taken a different approach. Ironically, they're open source. So not OpenAI, they're closed. Basically their language models are obviously training off the massive amounts of data that they have.
Yeah.
It's quite good as well, but it's not at the level at which OpenAI is at, right? Who else you got? You got QN, which is Alibaba in China, as well as obviously Deepseek. But Deepseek is a little bit different because they're not training the foundational models, right? So they're not going get everything on the internet in the world, compress it into this large language model. The reason why they're so good is actually the post-processing. So once you've actually trained this big knowledge, imagine this big knowledge tree that you've compressed into this language model, there's a lot that comes out afterwards that makes it great in terms of retrieving the right information.
Okay, so maybe an analogy would be Deepseek has taken high school kids and put them through college, and they've come out more specialised or even smarter.
I guess that's one way to see it. It's like it's taken an uncut diamond and polishing it up.
Yeah. Right? And that's kind of where so that's the next part here, and that's obviously where DeepSeek's come in. So DeepSeek came out with their R1 model. I think I came across it back in, I think it was 2 weeks ago on a Monday. I was talking to a friend who actually builds data centers for large corporates, and I was like, there's an AI model that's 95% cheaper. And so him being American and the offering was Chinese, he was instantly dismissed it and just said, yeah, I don't believe that could be of any quality. And I'm like, oh, okay, fair enough. And then lo and behold, about a week after or a week and a half, the market actually cottoned onto Deepseek. And then that's when NVIDIA had that first 17% drop in value. I think it erased $1 trillion in value. I forget the exact numbers. But so my interpretation of it is that, so Deepseek, they came out and they said, we only spent $6 million, and everybody instantly got their minds blown that, like, you know, America spent hundreds of billions of dollars, and some lab out of China of super smart guys spent only $6 million. That's the headline though, and a lot of people interpret it the wrong way. And then, as Kai is trying to explain, that's actually just $6 million in post-training.
Yes.
Yeah, and this is the key, is that they've made a model that's a lot more efficient as well, and they're able to offer it at a much cheaper pace.
Yeah, like if we go and, like, we can go really down into the weeds here, but I'll try not to do that, right? But like, essentially, because we should talk a little bit about the hardware and what it means. Why do we need GPUs? What's
okay, yeah, well, that's a good point. Because I'll just bring back to what I know about GPUs. Is that, so from my crypto days, obviously. So Bitcoin is on this SHA algorithm or code that, you know, you pretty much just have to brute force these calculations to get a key to unlock the next block. And then that's kind of like the basis of the actual blockchain security. What people figured out was, like, hey, GPUs are really good at just doing this one calculations, and that's where NVIDIA actually had their first bump, because they had the best GPUs, but no one was using them. You know, most people were using for games. And then once Bitcoin miners found them to be really efficient to mine Bitcoin, that's when their share price had their first bump. And that was actually by accident. But yeah, so that's where GPUs come in. So that's my limited knowledge on GPUs.
Well, no, you're right.
Could you expand on that?
Yeah, no, you're right. Like, in the sense that GPUs are incredibly efficient in terms of processing a lot of data, right? I mean, you know, originally, obviously, they're for games. You know, there's a lot of calculations in terms of the imaging processing and that stuff. But it just so happens that basically, like, it does a lot of calculations, it has a lot more cores than CPUs.
Yeah.
Right? So the compute power is, you know, well above what the CPU can do, right? So with these large language models, because they've got so many parameters, so many things in there, you need a lot of processing power.
Yeah.
Right. So hence GPU. Right. But, you know, basically, NVIDIA has almost a monopoly in this AI market. Not necessarily in on gaming, obviously, like AMD's out there. So, you know, a lot of people make comparisons of why can't AMD, and they are getting better. They're actually not too far, but it's possible to do language model processing on AMD chips, GPUs. But the issue is actually the software that controls these GPUs, right? So for NVIDIA, like, you see these massive data centers with 100,000 GPUs, they all need to be linked, right? So if you put these language models or all this, just make it simple, and all this information, it all has to come together in some way.
Yeah.
And, you know, at a hardware level, this thing is going crazy, right? So basically, the software that NVIDIA releases controls all these hardware, and it allows clustering of the GPUs efficiently. Yeah. So that calculation you can expand and scale out to a massive scale, right? AMD, the software for AMD is not there, right? It's not as good. They're getting there. They've come out with ROCm, which is their.
So interesting. So it's actually, NVIDIA doesn't have a lead in the hardware. It's actually the software part.
They do have a lead in hardware as well, but it's not as dramatic as what it is in the software, right? The main constraint is actually the software. It's not the hardware. I think AMD could probably get to a state where it's competitive with NVIDIA, but the issue is the software.
Yeah. Okay.
Right.
Great. So,
And going back into Deepseek, right? And the reason why they were able to achieve this crazy cheap cost is because that they're actually optimizing at a layer below CUDA. CUDA is the software basically that manages all the processing in NVIDIA GPUs, right? So basically they've written to a level below CUDA where it's way more efficient than using NVIDIA software for that specific purpose. So this is going a little bit more into the weeds, but like I'm not going to go too deep. It's called MOE, multiple evaluation, but it basically they compartmentalize which segment of the LLM to train, but it's not very efficient with the default software. It's not very efficient in terms of passing it to all the segments of this model to train, right? So basically it becomes lopsided. All the data goes in, and you feed it into a couple of these segments, and the rest don't get used, right? So the overall training it's not as efficient. But with them writing basically directly to the card, they're writing their own hardware level code, right? They can absolutely optimize in terms of how efficient that model is trained. It's just way better.
Yeah. Okay. So that's, so the way I see it, Deepseek's come in, and as you said, basically they've democratized AI for everybody. So
it's quite right.
That's the biggest thing, is that so the way I interpret it is that Sam Altman, he was on the path to, we need more money, we need more hardware, we need better hardware, we need more money, basically. And what China's done is that just through smart software, which you explained, they're like, no, you actually don't need to use all that brute force, and here's a slightly more efficient, a different way of doing things, but it is more efficient. And
well, to be fair though, Deepseek doesn't focus on foundation models, so that they don't go process every single piece of information on the internet and condense it into a model, right?
Mm-hmm.
Still, that only the frontier models can do that, and that's why it costs so much. For these bigger players to create these foundation models, but they kind of just tacked along because they'll use Olama, they'll use QN, which is all open source, where these bigger players have consolidated all this information, and post-training is basically where they're really making the mark. So I'll talk about in terms of a little bit about performance, right? So, the amazing thing is it's not really. You compare DeepSeek R1, the reasoning model, to OpenAI's, or at the time it was O1, the frontier model, right? It beat it slightly in some metrics. Overall, let's just call it they were on par, right? Mm-hmm. So in terms of pure performance, it wasn't massively ahead of OpenAI.
Yep.
But the beautiful thing was obviously, as you say, the cost, right? So for us, when we're using API calls to OpenAI, if you're using O1 model on the pro level, it's $60 per 1 million tokens. Mm-hmm. So basically 1 million words for $60, right?
Yeah.
These guys, 1 million words, $2. Right.
So let me use my AI. So $2 versus $60. Yeah, I know which one's cheaper. But
right.
The whole point is that it's significantly cheaper.
Yeah.
And as I said, it's democratized AI now.
Absolutely.
Now everyone has access to it. Kai's already setting up a GPU for us in here just to save money and use AI in-house.
Yes.
And we just figured there'll be a lot of smarter guys as well that will use this access, and it's just really opened up the game here. So it's quite amazing what they've done. So just going on to that, so now that we've got cheap AI, we've got all these large language models, we've used neural networks, we've got all these data centers built up, and now we've found a more efficient way. Mm. Will AI become sentient? Should we be afraid? We've all watched Terminator 2.
Oh, of course.
We've all seen what Skynet does.
Well,
is that moment coming, basically?
As Elon puts it, it's a non-negligible probability.
Yeah.
And it's true, right? I think with obviously the models now, right? I don't really think it poses a safety threat, but this is one of the key questions in the next decade. Based off what basically all the experts are saying, it's within the next 5 years, artificial general intelligence (AGI), probable. Within the next decade, everyone's betting that it's for sure coming. So, and what is AGI? Basically, to put it simply, it's AGI is generally the skills of that model is equivalent to a human being or above, right? And it's then what everyone's afraid of is it's not a big step to go from smarter than a human being to super intelligent.
Yeah.
So, and this is where really the existential risk for us comes about, right?
Mm-hmm.
You know, well, how do we know that AI is actually aligned with us? Skynet example, you know, it's like, well, humans are inefficient, why don't we just go on?
Exactly. So that's exactly. So that's a philosophical question. I mean, like, but the thing is, like, yeah, we're going to that point, so we will run that experiment.
Well, it's running in live, right?
But that's what I'm saying. Like, so that whole Skynet thing, like, we might joke about it, but yeah, a computer will reach that point fairly soon.
Oh, it's definite, right? Like, so the genie's out of the bottle. It's like, it's the same with nuclear weapons, right? Like, you know, once the technology, this is all throughout human history. Once a technology is possible, it is definitely going to be explored, and it is definitely going to be unlocked in some way.
Exactly.
Right?
So let's just hope we have some responsible humans that are at the forefront.
Let's hope so.
Let's hope so. So yeah, so that's so before we move on, so obviously today we've talked about AI for dummies, and we want to just break down sort of the whole AI landscape. So the way I envision it is that you don't have to know how an engine works or how a car actually works to actually sit down behind it and, you know, press the accelerator and use the steering wheel. So, but what we wanted to do is, because AI is such a sort of complex topic, and a lot of people are kind of afraid to ask, this is kind of what we wanted to break down. Now, as investors, if you actually want to, you know, use this extra knowledge that you've gained today, we actually have another webinar where we talk about the investment, you know, sort of landscape, and where you can actually, you know, invest and try and profit from this AI movement.
Right.
Yeah, and so that's on our website. We'll have a link to that somewhere on the page, so just click on through. And if you have any questions, these are our contact details here. So the main one is the email, invest@mpcmarkets.com.au. So just in to top it, to finish it up, do you have any sort of summaries for the folks at home, Mr. AI Genius?
Oh, stay safe. Hopefully Skynet doesn't come. No, I think, yeah, in terms of investment landscape, you know, I'm quite bullish on that. I think, you know, I love the open sourcing thematic of it, right? Because I think you know, it does allow it to be democratized, as well as, you know, just more outreach to more users, right? It's same with Android, same with Linux, all these things. Basically, Olama, which is basically what Meta's working on, it's going to be the OS of LLMs.
Yeah, absolutely.
So,
okay, great. Well, if you have any questions, just send them to invest@MPC Markets, and thank you for viewing, and you have a great day. Thank you.